about to start where you left off in our block classes, I do want you to review a couple of things first with our exponentials. So you can look at your 11.1 and 11.2 notes for these review things. Once you finish this, you'll move on to your 11.4 that you left off with. So a couple of things I want to review first. So there's a couple of things I want to talk about with linears, and then we can talk about with exponentials. So remember, with linears, you are basically adding or subtracting the same number each time. So that a situation with a linear would be something like you are babysitting and you get $5 an hour. So you start with $0 and then you get $5 for the first hour, and then you have $10 after 2 hours, and you have $15 after 3 hours. Maybe you are getting a gym membership and they a lot of times charge a fee in the beginning. So they charge a $40 sign-up fee, and then they charge you $25 per month. So you pay $40, and then every month on top of that, you pay an additional $25. So $40 and $25 in the first month, but then the next month is just $25. And then in the next month, just $25. And then in the next month, just $25. And that is a linear, okay? With linears, when you graph, you get a line. Graphing gives you a line. You saw your diagonals going in positive or negative directions. Remember, you also saw horizontal and vertical lines, your y equals or x equals equations. Your parent function was just simply y equals x. And then from that, you have your different transformations that you could do. You change your slope, you change your y-intercept to change that equation. Your domain in this case is all numbers. Remember, domain is dealing with x. So we usually write it down as negative infinity less than x less than infinity, but that's simply just saying it's all numbers. And the reason for that is because your line is extending forever and ever left and right. And then your range is actually the same thing. Remember, the range is talking about your y's, whereas your domain is talking about your x's. So back up with domain. We said that your graph is going left and right forever and ever. With your range, because it's y's, we're talking about your graph going up and down forever and ever. And so if you had a graph, all linears look something like this with arrows on the ends. So they're going left forever and right forever. They're going down forever and up forever. Okay. Same with if I would have a graph that looks like this. Same thing. Okay. So now let's review the bigger topic here, your exponentials. So this is what we left off with, or what you left off with before all of this happened. So with our exponentials, a couple of things. First, linears, you're adding the same thing each time or subtracting. With your exponentials, you're multiplying. So there are lots of great examples of exponential functions, and you know what? We are currently living in one. One person had the coronavirus. They spread it to 2 of their friends. Then this person spreads it to 2 of their friends, and this person spreads it to 2 of their friends. And then this person spreads it to 2 of their friends, and this person spreads it to 2 of their friends, and this person spreads it to 2 of their friends, and this person spreads it to 2 of their friends, and so on and so forth, and there's your exponential. Now, there are definitely a lot of real-world exponentials that are not perfectly exponential, and this would actually be the case because maybe this person right here actually has a job to where they're going to spread it to a lot more people. And so then they would, spread and spread and spread. But this person right here has a job that they're able to work from home and they isolated, and I guess I should keep them because, yeah, they got it, but they didn't spread it to anybody. And this person self-isolated and only spread it to their significant other. And this person also self-isolated and they didn't spread it to anybody. So each row is still increasing. In real world problems, it's not always increasing by the same amount, but there are definitely some that do increase by the same amount in each row. When we talk about cells separate and form new cells. You learn that in biology. We start with one cell, and then this form splits into two cells. And it always splits into two cells. It doesn't split into 3 cells on accident. It doesn't ever not split into 2 cells. So then this one will come and split into 2 cells. And then this one will also. And they will continue to do that. This, your cell splitting, is a perfect example of exponential. You're timesing by 2 each time. Whereas the spread of the coronavirus is exponential, but it's not a perfect exponential model because it's not going to be multiplying by the same amount each time. It will just be increasing and increasing somewhat multiplicatively, but not exact. Okay, so let me get off of that little bit of tangent on there, and we can continue with this. So exponentials are multiplying. Let me come back. Your graph, we don't have a specific name to the graph shape, but I will just remind you that your graph is kind of this swooping, it will look like this, where it's increasing everywhere. Or your graph might come in and look something, whoops, let me undo that. Or to be decreasing everywhere. Okay, if you recall for this one, we call this one growth. And we called this one, the other one, decay. This graph is growing, it is increasing everywhere. This is where your cells are splitting and they're multiplying and they're getting more and more and more of them. Your decay is where it is decreasing everywhere. Your graph is getting smaller and smaller. It's kind of like you're dividing, or maybe you're timesing by some fraction or some decimal. This would be an example, like maybe you took some Tylenol at 8 a.m. this morning, and then every hour or every however often it is medically, it's the dosage left in your body is half. So if you started with 600 milligrams, then after, I don't know, maybe it's 2 hours, there's only 300 milligrams. And after 2 more hours, there's only 150 milligrams. After 2 more hours, there's 75 milligrams, so on and so forth. Okay, that's your exponential decay graph. We have a parent function, which I'm just going to have to write because I can't do exponents on this screen. It is y equals b to the x. This is your parent function. Remember that b is just going to be some number. So maybe it's y equals 2 to the x, y equals 5 to the x, y equals 1 over 3 to the x. This is your general parent function. We're going to wait and talk about domain and range in a moment. We'll do that a little bit more in detail because it's not as simple as all numbers for the domain and for the range. Okay. All right, so next thing, let's continue on with your exponentials. Next thing that I want to talk about is your general form for graphing. And we didn't, I don't think, ever officially give this, this way of writing this. You won't have to worry about creating all of this. You're going to be able to use Desmos to help you and all that stuff. But this is your general form, which, if you recall, our absolute values look like this, and our quadratics looked like this, and they're the same. Okay, they're just different places, but A, H, and K, they do the same thing. Your A is your dilating, your H moves you left and right, and your K moves you up and down. The important one to look at here for graphing information is actually B and K. Those tell you the two most important pieces of information for your graph. So B tells you if it's growth or decay. Remember that if B is greater than 1, it is growth. So if you have like 2 to the x or 5 to the x, that's going to be a growth. If your B value, however, is between 0 and 1, so you have a B value of like 1/2 to the power of x or 0.7 to the power of x, that is going to be a decay. So then that would tell you what type of graph you have, your growth graph versus your decay graph. So if your B value, if you have something like y equals 3 to the x, is growth, look like this. If you have something like y equals 0.3 to the x, that is your decay because it's between 0 and 1, and it looks like this. The second one that is important is that k value at the end. That tells you that horizontal line that your graph is never going to cross. So right here, if I have an xy axis, remember that there is a horizontal line that your line is never going to cross. That k value tells you what that value is. Right now I don't have a k value, which means that's 0, so it's never going to cross 0. If I have an equation such as y equals 2 to the power of x plus 3, I can get two very important pieces of information from this. This 2 tells me it's growth, and the 3 tells me the horizontal line y equals 3 is where it'll never cross. So I can make a quick sketch of this. Your graph will never cross this line and it's going to be growing. So I know it's going to look something like this. Okay. If this was a -3, it just would come down here. It would be -3. And it would still go in that same upward growth direction. If this was a number between 0 and 1, if this was 1/2 x plus 3, then instead of being a growth and never crossing here, it would come in the opposite direction and look something like this, be a decay and never cross that line. Okay. Now, there is one more thing that you're going to see on the practice IXLs that I want you to do with this, and it deals with this A value. Remember back here with your absolute values in your quadratics, if A was negative, it flips your graph. So in our absolute values, which look like V's, if it was negative, it's going to be an upside down V. In our quadratics, which look like U's, if A was negative, it's going to make your U upside down. Okay. With exponentials, that's the same concept. It's going to flip your graph upside down if A is negative. So if you have something like y equals -1 times 3 to the x, and you will actually see this -1 here. It won't just be a negative sign, because it's -1 times and then it's 3 to the x. So 3 to the x looks like this. -1 times 3 to the x doesn't change this line, it never crosses, but it flips your graph upside down. So instead of being here and up, it flips it upside down. So it looks something more like this. It still never crosses at 0, but now instead of going up for our growth, it's going to go down. Okay, same thing would happen, oops, with any of these graphs. If I looked at this one right here, remember was your 2x plus 3. If I made that -1 times, then basically it's going to take this graph right here and flip it upside down. So it's still going to be up 3, and here's the line it's never going to cross. And because it's 2, it looks like a growth initially, but now upside down, it'll look like that. Okay? All right. Next part, our domain and our range. So these ones we need to talk a little bit more about. The nice thing is domain is still easy. You come back and look at any of these graphs. Domain is your x. How far left is this graph going and how far right? Well, everywhere. How far left and how far right? How far left and how far right? How far left and how far right? It's always going to be all numbers. Because your graph is always going to go left forever and right forever. Range, however, is going to change because there's going to be a certain place where your graph stops. So when we saw this example here, we said it stops right here at this line. This red graph right here, we said stops right here. So your range is going to have a stopping point, and it just depends on where that is exactly. So for your range, let's say we're looking at the graph. For the most part, it's going to be y is greater than some number, where that number is the value of the horizontal line. So let me draw you in a quick example. That's a bad example. So right here, with this graph, it's never going below y equals 2. So my graph shows me my range is y is greater than 2. It's not equal to 2 because remember, it doesn't ever actually cross this 2. So it's y is greater than 2. Okay. If, however, we're looking at from the equation, it's going to be y is greater than k. And remember, back up here, we saw this k value. It's whatever we have here at this end that we're adding or subtracting or whatever. So a couple of examples with that. Let's say I have y equals 2 to the x plus 3. Lets me know that my range is going to be y is greater than 3. If I have y equals 0.4 to the x minus 5, then y is greater than 5. Oh, negative 5. Negative 5, because minus 5. Last one. If I have y equals 3 to the x, then y is greater than 0 because we don't have a number right here. Okay, it doesn't matter what number you have up here. Maybe I have x plus 2. That doesn't change anything. Maybe I have plus 1 up here. Doesn't change anything. What matters is your k value. This is your h value, which doesn't change your range. Okay. So I believe that is enough to get you through at least the first couple of IXL, so I want you to try those. And then there should be another video that I'm making about 11.2, more 11.2 information with your word problems.